is a problem where we have, this is called a velocity selector, because only charged particles with a certain velocity will make it through. That's because there's an electric field overlaid on a magnetic field. TVs and some other older TVs, CRTs, work this way. So an electron moves into an area in which the magnetic field is pointing into the page. So you could put your fingertips into the page, your thumb would go to the right, and your palm faces up toward the top of the page, meaning that magnetic force would put a force, and they have it here, QVB, upward on that electron, or I'm sorry, this should not be electron, this should be proton. So I'm back, and we actually have, I actually changed it to proton. For it to work with an electron, I'd have to have the, I think I'd have to have the electric field upward for it to work. Would that be right? Yep. So we're going to change this to proton so it'll work out. Anyway, the electric field, of course, is going to pull the proton down toward the negative area. That's the electric field, but the magnetic field will push it upward according to the right-hand rule. Well, we know that the electric force, based on the electric field, we know that E equals F over Q. Therefore, F equals EQ. That's for an electric field. And then we know that the magnetic field is QVB. Well, if those forces are equal and opposite, like this right here shows, for it to make it through, they got to be equal and opposite. Then I can just set EQ equal to QVB. And of course, the charge on a proton is 1.6 times 10 to the negative 19th. So the charge doesn't matter because that cancels out. And if I solve for V, I get E, electric field, divided by B, the magnetic field, and that's the equation for a velocity selector. So that's if you're mixing electric and magnetic fields. And so what do we have here? We have 10,000 newtons per coulomb. That's the electric field, divided by 5.0 teslas, and that's going to give us a velocity of 2,000 meters per second.